Hello everyone, welcome back. In this video, we are going to talk about how to explore data. So we'll cover exploratory data analysis, or EDA as it is called. It is generally the first activity to be performed to get some high-level understanding of new data, and it uses a variety of summaries and graphical techniques to just get a sense of the data, to get a feel for the kind of data that you have. And normally, the way the movie plays out is like this: your boss or your client or someone else who you work with, they give you some data or they point you to something, maybe on a thumb drive or on a Dropbox location or on Google Drive, to say, hey, there is some data here relating to complaints or customer calls or something else. Can you have a look at it? And that's the kind of situation where you would have to first get acquainted with the data through the process of EDA. Now, the goal for EDA is to interrogate the data in a very open-minded way. And the goal is to obtain a high-level understanding of what the data is, what kind of themes might exist in the data, what are the important variables, are there any very obvious anomalies, are there missing values that are just obvious that you can see when you go through the data. Review the data types, get some visual understanding of the shape of the data, by which I mean the distribution of the data, understand correlations between different fields in your data. So those are all the kinds of things that we would look at as part of our EDA. Now know that all of these things that I just talked about may not be discoverable just as part of an EDA, and you may have to do more work afterwards, but they are generally the kinds of things that we look out for when we perform EDA. And EDA, as I mentioned, is unstructured exploration. There is not a set of set activities that you must perform. So there isn't a list or a sequence of things that you have to do. You probe the data, and depending upon what you find, you ask more questions. So with that overview of EDA, let's launch into some slides now. And I will first begin with providing a quick overview of descriptive statistics. Yes, these are the same ones that you probably looked at when you were in high school, but a quick refresher. Now, this time, not a mathematical refresher, but a conceptual refresher of what kinds of descriptive statistics are available. Descriptive statistics are data summaries, how to interpret them, how to use them. So let's look at that. So here is a slide on descriptive statistics. As I mentioned, descriptive statistics are key summary attributes of a data set. They include things such as mean, median, mode, and they give you a high-level understanding of the data very quickly. They are abstractions at the highest level, and you don't have to do a lot of work to calculate them. And they're also a very effective way of communicating the essence of the data set. So when you are speaking about the data to someone else or explaining it to a client or to a manager or to a colleague or another team, you can tell them, this is the average of the data is this, and so on and so forth. But at the same time, because they are summary quantities, they also have limitations. They hide a lot of the complexity that your data might have. So we will look at some of this stuff when we get into the video on EDA. So what kinds of descriptive statistics are available to us? So we have averages, and these are also called measures of central tendency. And they are called measures of central tendency because they try to find the center of the data, which is through averages or finding out the median value. They also look at how spread out your data is uh, compared to your mean, compared to your average. And that is expressed very often, as you would know, as a standard deviation. So we will look at how to interpret standard deviation, not just the formula, but how to actually use it as well. Then correlations. So if your data is not just a set of one type of values, but it has several values relating to whatever the topic is that you are analyzing, then what are the correlations between the different fields that you have access to as part of your data set? And then we can also look at the shape of the data sets spread, for example, by looking at percentiles, quartiles, etc. So we will look at all of this stuff as part of this video. Now, those who are interested in code, There is another video that is going to cover how to actually calculate them using Python and pandas. So we will, everything that you will see on these slides, you will find that there is code to back it up. So it's not just discussion at the highest level. If you want to get your hands dirty, the code is there. So we will cover, as I mentioned, most of the common uh, measures for descriptive statistics, and let's launch right into it. Mean, I'm not going to spend too much time on it. We use it every day. We look at it all the time. And this is really just the average value for a variable. You sum up all the values and you divide by the number of terms you have in your data. Then there is another thing called geometric mean. And this is the nth root of the product of n values. So if you have 5 values, you essentially you multiply them together and you take the fifth root. So you raise it to the power of 1 by 5. And this is normally useful for data where data is changing by a certain growth factor from one period to the next. So for example, if you have, and there is an example right here, there is a mutual fund that provides you a certain set of returns over 10 years. And the question to you is, what is the average rate of return from this mutual fund? Now, the answer to that question is not going to be a simple average of all of these returns over these years. You will have to calculate a geometric average, and we will see how. So, for each year's returns, you have a multiplication factor, which is really just the return plus 1, and that adds up to 0.786 for the first year, which means if you had $100 in the investment at the beginning of the year, you are left with $100 times 0.786 or $78.6 at the end of the year. Next year, you begin with the $78.60 and you get a 29% return, and your multiplication factor would be 1.293 and so on. So, and here is a table that clarifies this. If you want to understand some more of this or want to try this, you can pause the video and you can check this out yourself as well. Now, if you look at the simple averages, the simple average of all of these returns is 5.54%, but that is not the actual return that you are getting each year from this mutual fund. The actual return is given by the geometric mean, which tells you that the return is actually 3.45%. And you can verify that by multiplying your $100 and multiply it by 1.0345 to the power of 10, and you get $140, which is here. And this is the same as this that you are left with here. Another measure is the harmonic mean. This is the inverse of the average of inverses. I'm not going to spend a lot of time on this because this is something which has some very unique and very rare uses, I would say. So for example, if you're trying to solve problems of speed, average speeds, then you can do that using harmonic means, but you can also do it in a very regular, simple way, into a more intuitive way, using a simple calculator as well. Next measure that for descriptive analytics would be the median, and we are very familiar with this. Median is really the middle value when all observations have been sorted in some order. So if you have, for example, if you have 5 values here, just like you see here, the median is the middle value, which is this one. If the number of observations is even, then just like here, then the two middle values are these, and the median would be the average of these two, which is 62. And here is a real example of a median, something that we can relate to. Median household income, according to the United States Census Bureau, was $70,000 and something in 2021. And what that means is half the households made more money than $70,000 and half made less than 70,000. So this is the middle point for incomes. This is not the average income. This is really just all the households and what does uh, the household sitting right in the middle of the distribution make. And that's median. Mode. Mode is the value that occurs most frequently in a data set. And this can be quite useful sometimes to understand as well. So if you have a data set, for example, that looks like this, 5 values, just for the sake of simplicity, then we see that the value 61 appears twice. That is the most occurring value, so 61 would be the mode. In reality, however, our data sets tend to be much larger than just 5 numbers, and they would have thousands, millions of values. And when we plot them out, we get graphs like this. So what we have here are histograms. So these are histograms of our data's distributions. And we find that these would be what we call multimodal distributions. Multimodal meaning that they have more than one mode value. So if you look at the first distribution, you might say that this is your modal value because this is the one that occurs most frequently and definitely not this one. However, the way the data is organized, and if we look at this particular range of the data, then this is actually a pretty important data point for us here. And therefore, this is also in some ways a modal value of sorts. In this data set, again, we see the same thing here. Even though this may be the highest point in terms of the number of occurrences, these values are also equally important in some ways, and these would be interesting to know about as well if we are analyzing the data. And these are what we call uh, bimodal or multimodal data sets. Next, let's look at measures of variability. So we look at things such as range, variance, and standard deviation. Range is really just the difference between two values uh, and refers to the in the context of a measure of dispersion, it refers to the difference between the maximum and minimum value in the data set. So if I have a data set, for example, that lists prices for a set of diamonds, then and the most expensive diamond in my data set costs $18,000 and the least expensive is 300 odd dollars, then my range is something like 18,497, and that would be just the difference between the maximum and the minimum. So at this point, because I'm talking about diamonds, let's just talk a little bit about the diamonds data set that we will be using often in these videos to illustrate some concepts. So the diamonds data set is a data set that was curated by Hadley Wickham and others and published open source, available to everyone. It has records for about 50,000 diamonds, actually 53,490 to be precise. And every record is a line item representing a single round cut diamond. It has a number of attributes that you can see on screen. It lists the carat, the cut, color, and clarity for each of the diamonds. And then there are some specific technical measurements of the diamond, which is table, price, X, Y, and Z. And we have a data dictionary here that explains what each of these different fields mean. On the right here, you see an Excel view of that data. Note that it only goes up to 42 records because that's all we have space to show. But this data set, as you can imagine, is reasonably large. It's got 53,000 records, and it gives us information on all of these diamonds. So we can experiment with this to try out concepts and ideas and illustrate things that we want to look at. And that's what we will be using for some of these videos. Now, going back to standard deviation. So standard deviation gives us a measure of how much on average is our data spread out when compared to its average. And what does that mean? Normally, one would expect that your data is centered around the mean or the average. all of the data points, like they would be close to the mean, but some would stray away from the mean and would be further away from the mean than others. What is the average deviation that they have when compared to the mean? How far out they are on average? So that calculation is what is expressed as standard deviation. Now, one would think that if all I all I do is I find out how far away each data point is from my mean, and I take the average of those distances, then that'll give me my standard deviation. Unfortunately, mathematically that does not work, because when I add up all the differences from the mean, they add up to 0. So in order to take care of that, I have to square my differences, add them up, divide by my number of observations to get what is the average squared deviation, and then take a square root of that to find out what's my standard deviation. And that's why it's called a standard deviation. Related measure is the variance. The variance is nothing but the square of the standard deviation. Standard deviation is measured in the same units as my original data. That makes it very easy to interpret. Variance, on the other hand, is measured in units squared, which makes it a little bit more difficult for humans to interpret. So I am not going to spend more time on variance at this point. Whenever you see a variance number, you can take the square root of that, get the standard deviation, and that will probably give you a more intuitive understanding of what the deviation from the average is and how dispersed your data is. So going back to the slide, this is the formula for standard deviation. But what is standard deviation useful for? So when somebody gives you a number for standard deviation, how are you going to measure it? Like, what are you going to do with it? That's really the question. So the answer to that is there are two rules that you can apply in order to interpret standard deviation. The first is what is called the empirical rule. For a normal distribution, approximately 68% of the data is going to lie within one standard deviation of the mean. So if your mean for, say, for example, SAT scores is 1300 and standard deviation is 100, then you can imagine that uh, 68% of the students have scored something between 1200 and 1400, and so on. And almost all the data values will lie within plus or minus 3 standard deviations of your mean. Now, this is based upon the assumption that your data is normally distributed. That is a very strong assumption, and that may not always be true. In fact, for most data, you would have no idea whether your distribution is normally distributed or how far is it from being a true normal distribution. And there enters Chebyshev's theorem, which is actually much more applicable and useful. And this is something that I always keep in mind when someone gives me a number for standard deviation. So this is a lot more relaxed than a normal distribution. And really what it says is that 75% of your data would always lie within 2 standard deviations of the mean, no matter what the shape of your distribution is. Now imagine that is a really powerful thing to know. So if you know the standard deviation for the data, and if you know the mean, then you can do a plus minus 2 times standard deviations of the mean and be sure that 3/4 of your data lies within that range. And that gives you a lot of power. Now, that actually can be extended to other uh, multiples of standard deviation as well. So 8/9 of your data would lie within 3 standard deviations of the mean, which is why 3 sigma is so cited when people talk about data, because most data, no matter what the shape of your distribution, would lie within 3 standard deviations. And that can be generalized to 1 minus 1 by k square of the data lying within k standard deviations of the mean. So this rule is extremely important, and I would, as practitioners and as managers, as leaders, I would really like everyone to keep this in mind. This is extremely powerful. This part is extremely powerful and very useful to know. We have covered a lot of material and context on descriptive statistics. Let us take a pause for now and meet again in the next video where we will cover the concept and the ideas behind correlation. In the next video, we will conclude our discussion on descriptive statistics, allowing us to move on to analyzing and exploring the data. See you then.